We no longer build massive structures by looking at paper blueprints. Today, a building exists completely in the digital realm as a comprehensive digital twin, long before a single shovel hits the dirt. A single modern skyscraper contains millions of individual digital data points, logging everything from the primary concrete foundations to the exact placement of individual light switches. Dozens of independent disciplines create this data simultaneously. Architects, structural engineers, and mechanical contractors all build their specific pieces of the building at the exact same time. But if you attempt to view all those disciplines' data at once, the system collapses into visual chaos. The building becomes a black, impenetrable mass of overlapping lines and solids. Inside that mess, severe physical errors hide in plain sight, like a mechanical engineer's air conditioning duct routing blindly through a primary load-bearing structural beam. If an unnoticed digital clash makes it out to the physical construction site, all the work stops immediately. Correcting that steel beam on the ground results in multi-million-dollar delays. Unorganized digital data represents a catastrophic financial risk. Navigating it requires a universal syntax to filter the chaos before the first foundation is poured. To force order onto the models, the industry relies on rigorous standardization, like the CP83 naming convention, which acts as a strict universal language for filing every single digital entry. Take a look at this layer name, A-wall-E-. The initial A instantly identifies the architect as the specific originator of the file, and wall tells us exactly what object we are looking at. That final E is the presentation type code. It stands for element. Filtering the model by the element code strips away all the surrounding noise, leaving only the pure, solid, three-dimensional geometry of the object itself. But an element evolves as a project progresses, the rulebook dictating exactly how detailed these elements must be at different phases of construction is called the level of development, or LOD. Looking at this detailed 3D model, we see the peak complexity of the element code. Early on, a beam is just a generic box. By LOD 400, that element must be modeled with every physical connection, support, and fabrication-ready steel gusset plate perfectly represented. These highly detailed elements give us the physical form of the building. But to actually fabricate and place them on a job site, that form requires exact mathematical structure. Workers on the ground cannot construct a building from a solid 3D shape alone. They need the underlying layout information. Looking at this wireframe outline, we see what happens when we toggle our presentation code to D for dimension. The solid object drops away, exposing the foundational geometric structure and the precise mathematical layout measurements. Even with precise measurements, a raw layout is insufficient for complex multidisciplinary coordination. It doesn't tell a mechanic where a fire zone starts, or an electrician where an exclusion zone ends. When we swap the code to A for annotations, the layout floods with hidden spatial metadata. Crosshatching instantly maps out the restricted zones and the safe corridors. Add the T, or text code, and we uncover the explicit, non-graphic specifications required by law. Callouts demanding 2-hour fire ratings, or high-grade steel pointing directly to those newly hatched zones. Separating data into E, D, A, and T layers allows a model user on site to select exactly what they need, completely bypassing the avalanche of irrelevant data. These presentation codes transform a purely visual 3D rendering into a functional, actionable set of construction instructions. These technical naming conventions act as the primary framework for the BIM particular conditions, the project's central legal contract. Because the digital data is perfectly siloed by the originator and presentation type codes, every architect and engineer retains clear intellectual property protection over their specific contributions. If a downstream contractor takes a structural model and makes an unauthorized modification to save a few dollars, the strict coding shields the original model author from the liability of that change. If a discrepancy or physical clash does occur on the construction site, these standards establish the hierarchy of truth. The naming conventions dictate exactly which finalized design file holds legal supremacy in court. By forcing designers to categorize their data into these strict codes, we translate digital complexity into a clear set of instructions for the physical job site.